All right. Okay, let's take a look at a couple more today. And then you should be set to do a bunch of work. So I think here's where we left off yesterday. Did we finish that one? I don't think so. Oh, here's where we were. Right. So we found... So we had first derivative critical numbers at 4 and -4, right? So let's just add this stuff to our table. So -4 and 4, those were zeros of the first derivative. It's a polynomial, so the domain is infinite. And then second derivative, we left off here, right? Remember where we were? We were just looking at another polynomial, okay? So, what about this guy? Can we find? Probably not. Well, I bet we can. I bet we can factor this one pretty quickly. We could use quadratic formula, but let's just, this is good practice. So if we use bottoms up, what's A times C this time? -48?
Yes.
B is -8. Can you find factors of -48 that add to -8? I bet we can. Oh, yeah. Yeah. 12 and 4. There you go. So -12, +4, right? So we could go bottoms up, so we know that our magic numbers are -12 and 4. Should we go through one of these? This is pretty good practice, good review. So we're going to get x minus 12 times x minus 4, but then we got to divide each of those magic numbers by 3. We're going bottoms up, right? We're going to simplify. And then here we're left with a 4/3, so we'll go bottoms up, right? Okay, make sense? So what are my zeros going to be then?
4 and 4/3.
Okay, good. So f prime equals 0 when x equals 4 or x equals 4/3. Okay? And we didn't have to do that fancy factoring. We could have just plugged it in quadratic formula too, right? Okay, so then if we go over to next page, so 4 was a 0 of both derivatives, and was it 4/3 or -4/3? 4/3? Right. Oh. That should have, I messed that up there. That should have been a +4, shouldn't it? So that's going to make that a -4/3. So somewhere. Okay, so I picked this one on purpose. Now let's be smart about this. Let's be as efficient as we can. Remember, it's a general rule. We want to work further down in our table. We have less work to do. So what's our next step? Test points. Okay, what's the first test point we definitely want to use? Test point of the second derivative, keep in mind. Say it again. -4, for sure, right? Because then we get 2 birds with 1 stone, right? -4, we're going to calculate the concavity, which we need to know, right? We're trying to find, what are we trying to find here? Was it, I'm assuming, maximum, minima, that was it? Okay, they didn't ask for inflection points, okay? If they had, I mean, if we asked, which we're going to, in section 3.6, I want everything, right? I I want the whole works, I want inflection points, extrema, everything. So if we were doing that, you see why it makes the most sense to use this point right here, because we're figuring out two things at once, right? If we pick that test point, the second derivative at -4, what's that gonna give us? It's not factored here, so it makes it a little bit tough, but we're gonna get positive, it's gonna be positive, isn't it? Everybody agree? Right, I'm gonna get pretty big positive minus, it would be 16, right? We can already see it's gonna be positive. So what is that? By the second derivative test, what's that giving us? Right, if we have horizontal tangent and positive second derivative, that's concave up. Remember, that gives us a happy face, right? Positive second derivative at a critical number first gives us a happy face. So we got a maximum or minimum. What about right here though? This is indeterminate, right? This is the point I wanted to make. The second derivative test failed here, right? It didn't give us a positive or a negative sign. And so we still don't know what's going on at 4. It was a critical number of both. So what could it be?
It's, x to the third function.
But I don't want anything that specific. I just want to know if it's a critical number of the first and the second derivative, what could it be? Well, I mean, no, it can't be an asymptote because it's the function's defined there. But if it's a 0 of the first derivative, that qualifies it to be a candidate for what? First derivative, critical, there, what is it? Maximum or minimum. Could be an extremum, right? But it's also a critical number of the second derivative. So it could be an inflection point. Which one is it? We don't know yet, right? So what do? If we're looking for extrema, we could just test points around 4 and just go revert back to the first derivative test, right? So we could pick, for example, we could pick test values of like 0 and 10 or something, right? And let's go back to the first derivative, and I believe we have the first derivative factored, don't we? Yeah. There's our first derivative. Let's look at this part right here. We've got it factored nicely. Right, there's a factored form of the first derivative. So if we plug in 0, what are we going to get back? Positive, right? Positive times positive. So at 0, it's positive. At 10, it's positive. Okay? So what's that tell you? Is it an extremum?
No.
No, the function's increasing the whole time, right? That makes sense? What is it then? If it's not an extremum, but it has a horizontal tangent there, what must it be? It's got to be an inflection point, right? How can we tell? Well, we'll just apply those test points to the second derivative, right? The second derivative at 0 is negative, isn't it? Right? At 10, pretty obviously going to be positive. I'm going to get 300, actually, is it? Yeah, it is, isn't it? Right? So it is an inflection point, okay? So did we, now the books always tell you to go back to the first derivative row to check, they always say revert back to the first derivative test. Every textbook I've ever read says that. But I don't think that's the best idea. I think if you work further down, you get more information, because when we went to the first derivative row and we got plus and plus, we still, well, I guess we would technically have to, but we went down here and determined, is this an inflection point, right? If we had just worked in row 4, if we figure out that it is an inflection point, then it can't be an extremum, right? So we didn't really need that stuff. If it hadn't been an inflection point, let's just say hypothetically that had been negative and negative there instead of a positive, right? Well, then what does that mean? If the concavity is negative at all values up to 4 and negative for all values after 4, and it's negative at 4, and effectively that acts like a second derivative test, doesn't it? It effectively makes that 0 into a negative, right? And we could have said, okay, well then that means this is a maximum, for example, right? That's just that's just the way I mean, you don't have to do it that way. You're probably gonna be, I mean, you can always go back and revert back to the first derivative test. If you're just looking for extrema, well, I guess that makes sense. If you're looking for everything though, I would just work in that fourth row, right? Okay, but in this case, what we ended up getting was, so we can even draw a picture for this, right? We had a horizontal tangent, that's what the yellow told us. Right? And then the orange told us we're going from negative concavity to positive concavity. So can't we just do something like that right there? And we can see what feature that is on the graph. So while we're at it, what happened here? What happened there? What must that be? It's not a zero of the first derivative, so it's not a horizontal tangent. But it is an inflection point, right? It's a point of transition of the second derivative, so that is an inflection point. Does it look like this one? Doesn't, right? It's not a horizontal tangent, so it's going to be one where the tangent is tilted, but it's still a point where we're transitioning concavity, right? So that's a lot of information. Now, all we would have to do if we wanted to draw this picture is just add that into a sketch. I'm not even going to bother putting what the values of the function are at these places. Let's not even worry about it. Let's just draw a sketch, and we don't care if it's correct vertically, right? We could always anchor it with some points if we wanted to. But there's the y-axis, x-axis. We know at -4, we've got a minimum somewhere, so we'll just put it down here. Something like that, right? We have a point of inflection over here, and we have a point of inflection right here. Okay, so we're going to have to change concavity there and change concavity there. So it's going to do something like that. Does that make sense? That's our look. We could, like I say, we could anchor those points in some places if we wanted to, so we can make it look more exact. But that's the behavior of the function. Okay. All right. So, point of that one is, if the second derivative test fails, then you just have to pick test points around that critical number and determine using the first derivative test, for example, or even using test points in the f double prime row. What's really going on there, right? It was second derivative test was indeterminate. Okay, let's look real quick at just a couple, because I gave you some like this. I didn't just give you polynomials, I gave you a couple other functions to deal with too, right? Real calculus asks you to do stuff not just with, I know lots of times, just your calculus books just give you polynomials, but you gotta be able to deal with this stuff with other functions too. Okay, so first of all, what's the domain of this thing? This takes us back to kind of pre-calc stuff. Where does a log live?
Greater than 0.
Okay, so we know that the log of u is only defined when u is greater than 0, right?
So that's
So we know all this stuff in here, right? So 3x squared plus 1 has to be greater than 0. Right? Okay, so what can we get for this?
we go to isolate x.
Okay, we gotta just solve that for x, right? So we're gonna get 3x squared is greater than -1. When's that true? Always, isn't it? Everybody agree? Yeah. So the domain of this thing, even though it's a log function, the domain is all reals on this, right? Because as far as the log's concerned, we just can't give the log anything other than a positive number, but we always do, right? Because x squared is always positive for all real valued numbers, and if I'm adding 1 to that, right? It's always greater than 0. Okay? So our domain is everywhere. Okay? So then we're just going to kind of plow forward with the calculus, right? If we're trying to find where it's concave up and concave down, we're trying to find inflection points and stuff.
So if we're gonna be efficient about this, do we really even care about critical numbers of the first derivative? No, we don't, right? We just care about critical numbers of the second derivative, okay?
So first derivative,
One over which way is square plus one.
derivative of log u is,
One
well, u prime over u,
u
right?
prime zero, sorry.
So we get 6x over 3x squared plus 1 is our first derivative. If we were finding, I just wanted you to get a little practice with this. I'm not going to write anything down, but if we were looking for first derivative critical numbers, who can tell me where would I find, what are all the first derivative critical numbers? 0, okay. How come there's no, so the first derivative equals 0 when the top is 0. Would there be any places where it's undefined, where the bottom equals 0? Same reason as before, right? Bottom is always positive value. So we'd only get one critical number at 0 if we were looking for that,
Can
right?
you also justify that by saying if you set the entire function equal to zero, you just multiply zero by bottom and it goes away?
I'm not sure I understand what you're saying.
If you set that entire equation equal to zero and you attempt to isolate x, you could just multiply the bottom, both sides by the bottom, and give us a zero times the bottom equals zero.
Well, you could do that.
Well, but that's just reinforcing that the fraction equals 0 when the numerator equals 0, right? Yeah, I mean, you could if you wanted to. Yeah. Yeah. So then we got quotient rule, right? We're kind of stuck with the quotient rule problem this time. So what's quotient rule?
Log d high,
What's d high?
6. Minus I d low,
Okay, so somebody else, what's d low? There's somebody else involved here. What's d low? Emily, what's d low?
6 x.
Yeah. All divided by bottom squared, right? Okay, so we could, what could we do here? We could factor a 6 out of the top if we want to, right? We're gonna try to get this thing in factored form if we can anyway. So we could pull a 6 out of the top, and that's gonna leave us with 3x squared plus 1 minus, there's my minus sign. If I take a 6 out, what do I get there? 6x squared. All divided by 3x squared plus 1 squared. So that's going to give me 3x squared minus 6x squared. So 1 minus 3x squared. Everybody agree? Okay, so that tells us then f double prime equals 0. Let me say it out loud. I'm going to look at that for a second. When's that going to be the case? The top equals 0. And what's the part of the top? The top equals 0 when what happens? So where's the action happening here? Okay, so when the stuff in the parentheses equals 0, right? So we could probably skip clear up to the statement. The second derivative equals 0 when 3x squared equals 1, right? Isn't the top 0 when the two terms are equal? So we're subtracting. Okay. So in other words, when x squared equals 1/3, right? So x would equal plus or minus the square root of 1/3, which is just the same thing as 1 over root 3. We'll just leave the square root on the bottom, big deal. Right, just a number. Okay, so we get two critical numbers. So really all we have to do then is we're just going to make our table. And I can't stop myself from putting those rows. Just can't help myself because I know what we're going to be doing with them later. I don't want to get in the habit of leaving them out of there. But infinite domain critical numbers were, of the first derivative, are just positive 1 over root 3, so that's, you know, just some decimal between 0 and 1, and negative 1 over root 3. So what do I do to figure out where we get inflection points and to find out where it's concave up and concave down? Test points. Pick the easiest ones we can. What's one of them? Pretty obviously what? 0. Sure. So the sign of the second derivative at 0, I'm going to get well, I don't even care about what the values are, I just want the signs, right? Because it's in factored form, so I'm going to get positive times at 0, positive divided by positive, so positive. Okay. How about 1 would work? Sometimes I even do things like, I mean, 1 is fine, but I might even do something like 10, so it makes it really obvious, right? So at 1, bottom's always positive, the 6 is always positive. What about this though?
Negative, yeah.
That 1's gonna be negative, right? But notice that the second derivative is even, isn't it? All the powers of x are even. I get x squared and x to the zeros, where I get constants, right?
Yeah, so it's gonna be positive, negative at negative 10 and positive.
Okay,
10.
so then we could even just do something like that, right? The plus or minus 1. Either way, we're getting a negative result. And so that tells us everything we need to know, doesn't it? So let's interpret this. Now the question is asking determine the intervals on which the function is concave up or concave down. So based on this, let me color code this a little bit here. Oops. So those blue minus signs, that's supposed to be a plus. Those blue minus signs in this F double prime row, that's telling us that F is concave up on what intervals? Using intervals?
Negative 1 over square root of 3 and positive 1 over square root of 2.
Whoops, I meant to say down.
1 over square root of 3 to infinity.
Okay, and if we do them in order, I'm just going to have this whole interval over here, right? Which is everything less than negative 1 over radical 3. Right? Or, I can put an or symbol. A lot of times if we're using interval notation, we just ask for a comma like on that, and so that's fine.
Square root of 3 positive 70.
Okay? And then the green plus sign between those critical numbers is telling us that F is concave up on one interval, right? And we know here that we're getting inflection points at x equals negative 1 over root 3 and 1 over root 3. Okay? We get lots of stuff pretty easily from that table, right? Okay. Last one. Let's do an exponential one, how about? So, domain, right? So, are there any limits on the domain of an exponential function? Right, if we just graph the function y equals e to the x, doesn't that just look like that? Right? It's defined everywhere. So we got no problems with the exponential function. We got no problems with the x squared. So we got no problems, right? This thing is defined everywhere. So the domain's all real numbers. We've got to do a little differentiation here. So f prime, this is good practice. What rule do I have to apply there? Product rule, okay? Got a product of an x squared and an exponential, and then of course the derivative of 5 is 0, right? So we're going to get, I'm going to do the e to the negative 2x first times the derivative of x squared,
Yes.
okay? Plus
X squared.
x squared times the derivative of e to the negative 2x,
Negative 2x e to the negative 2x.
okay?
I mean, negative 2, my bad. Negative 2 e to the negative 2x.
I'm going to do it in layers. So we get the derivative of e to the u is just going to be e to the negative 2x times the derivative of negative 2x is negative 2, right? So it's a chain rule deal, right?
There's supposed to be an x squared.
Oh, what is it? And so then if we just simplify all this stuff, I'm just going to get 2x e to the negative 2x minus 2x squared e to the minus 2x, right? Let's pause there. What do you think? We're good from there. Okay, but we're trying to, now think why we're taking the first derivative, right? We're trying to find critical points for the following function, then we're going to use the second derivative test to determine what they are. But we're trying to find zeros of that first derivative, or if it's undefined, it's 2, right? So if we know we're trying to find zeros, what are we always trying to lean towards doing when we're factoring? Okay, Liz, you see anything I can factor out for both terms there? I can take out a negative 2x. I'll take out a positive, just because I got a positive. It doesn't matter, either one would be fine. So I can take out a 2x, that's good. Anything else?
E to the negative 2x.
Right? We've got e to the negative 2x in both of those. And then what's left behind if I do that? So from the first term,
1.
just 1, right?
Minus x.
Minus x, yeah. Can we see that? Okay, so then the first derivative is going to equal 0 when, by the zero product property, f prime equals 0 when
X equals 1.
I get 1 from there, right? Or 0 from there, right? Okay, makes sense? So I get 2 first derivative critical numbers, right? Now we move on to the second derivative. Remember when we're doing the second derivative though, and this is important. When we're doing the second derivative, I want to continue differentiating from the most convenient place. Well, it's not there, is it? We don't want to use product rule. We want to go up to where it's term by term. So we're just going to go from there. And I know that's still going to be kind of a pain. Well, you know what? Well, it's not going to be that much different, is it? So we've already done a little bit of this work, really, technically. There's the derivative. We already did x squared times e to the negative 2x, right? You could kind of recycle a little bit if you really wanted to. So here I'm going to get 2x times the derivative of, where are we here? E to the negative 2x. Let's just do that all at once. So that's going to give me e to the negative 2x times negative 2. plus e to the negative 2x times derivative of 2x, which is 2, right? So all we did there, right, we just broke this one up into those two factors. Now we got two factors there, right? You gotta do product rule again, so minus. Gotta be careful with these, there's a lot of stuff going on. Because I'm subtracting this whole function, I'm gonna, when I take the derivative of this, I'm gonna have to subtract the whole thing, right? So I need it in brackets or parentheses or something. So then I've got my, well, the same way. So we get 2x squared times the derivative of e to the negative 2x. Well, there's my negative 2 e to the negative 2x plus e to the negative 2x times the derivative of 2x squared, which is 4x. Okay, it looks like a lot of stuff, but really, that's going to work out fine. We're going to be able to factor out an e to the negative 2x from everything, right? And a lot of this is going to add up anyway, is it? Yeah. If I simplify this, this whole thing here is not going to be a negative 4x e to the negative 2x. Here I get a plus 2 e to the negative 2x. I've got to distribute the negative here, right? So I'm going to get a minus the negative is plus 4x squared e to the negative 2x, and then minus 4x e to the negative 2x. So look, those two terms are like terms, they add up. So let's do two things at once. Let's factor out e to the negative 2x. And then what are we left with? We're left with a 4x squared. We're left with a minus 8x. Everybody see that? I'm going to get a negative 4x and another negative 4x. And I get a plus 2. Yep. Sure. Okay, so there's the second derivative. I could take a 2 out of that too, couldn't I? And then I'm just left with 2x squared minus 4x plus 1. Second factor. 4.2, no it's not. Okay, so that's going to give us really inconvenient zeros, isn't it? That's not so good. It is kind of a pain. Right, so then this doesn't give us any zeros, does it? Right? This one does, though. So we know that f double prime equals 0 when 2x squared minus 4x plus 1 equals 0, which is going to be, by the Pythagorean theorem, when x equals 4 plus or minus the square root of 16 minus 8, right, all over 4. So what in the world is that going to give us? 1 plus or minus square root of 8 over 4. So that's 2 radical 2 over 4, so square root of 2 over 2. Did I do that right? I think I did. I mean, it's just math. That's not hard stuff. So we're going to get 2 zeros. We're trying to find where the function. Oh, we didn't even need that though. I was doing more than I needed to, right? You get that? That was kind of dumb, right? Because we're only looking for extrema, local maxima, local minima, right? Well, we only got. I mean, I didn't have to do any of that dumb stuff. Right? I could have stopped, technically I could have even stopped right there, right? Because all I'm doing is using the second derivative for the second derivative test. Taking it to there is probably an okay thing to do. But we don't need to do any of this stuff because we don't care. We're not trying to find
points of inflection, right? Everybody see that? So that really wasn't very smart of me. What were our first derivative critical numbers?
1 and 0.
1 and 0, right? So all we really need to do is right here, we're just going to check what's f prime of 1 and what's f double prime of 1, and f double prime of 0. F double prime of 0 is what? Yeah, 2 times e to the 0 is just 1, right? So we just get, it's positive. What about 1? Well, e to the negative, that's positive, right? So I'm going to get positive times, how about this thing in here, how about this factor? At 1, I'm going to get 4 minus 8 plus 2 is negative. So I'm going to get negative, right? So in our table, that's all we really need to answer the questions that were being asked of us. So we had 0 and 1, zeros of the first derivative, and positive and negative, so we know what those are. What's that one going to be by the second derivative test? Minimum, that's a maximum, right? We got it. Okay? Pretty cool, huh? All right. We did a lot of those, but we did a lot of those for a reason, because that's a lot of what you do in differential calculus. Like the big topic we're coming up on next is optimization. Optimization, we're just going to be, essentially, we're just trying to find peaks and valleys, right? And so we're doing a heck of a lot of this stuff using the first and second derivative test with real functions, that have actual meaning geometrically or economically or something, right? Trying to find extrema because they mean something important to us.
So, do you ever use a third derivative test?
No, you really don't. The third derivative test would be, you don't really, because it starts to get more, I wouldn't say never, but very, very rarely, right? And you would never call it the third derivative test. You would never do that. What you would do, if you were trying to find some bizarre mathematical relationship that was related to, let's say, the rate of change of the second derivative, right, for some reason, which you could do, then you would just treat the second derivative as a function and start again, right? And just optimize, optimize the second derivative. Okay. You don't just continue that with, really just have the first and second derivative tests.
Okay.